So let's look at this definition. This is what I just basically said to you a second ago. This is the notation, right? We started on the right-hand side here is what we started with when we were trying to find the inverse function, and we could not solve for y. So we just said, let's just use this notation. Okay? Now it says here, the domain of a logarithmic function is that x must be greater than 0. So I would like for us to go and take a look at that for a moment because it's super important. Remember, if our original function is a generic exponential, then the inverse of that function is the log base a of x, right? That's the original function, that's its inverse. Going back to last class, do you remember what the domain of this is? Think about the graph of a to the x. It either looks like growth, right, or decay. So the domain was always all real numbers, everything, right? And what about the range? This is important. Where do I want to? So assuming we're not shifting it, right? We're not shifting it up or down or anything like that. Remember what these functions can look like one of two things, right? It's either this or it's this, right? Those are the two scenarios. This happens when what? What's greater than 1? The a. When a is greater than 1, this is what happened. Oh, I said 1, wrote 0. We have growth when a is bigger than 1, so that number is bigger than 1, we have growth. And then this happens when what? Greater than 0, but less than 1. So like some sort of decimal or fraction. We have decay. So the domain is everything, right? Because the graph goes in both directions. But what about the range? 0 to infinity, not including 0, right? So, what about the inverse? What's its domain? What's its range? And why? So you have to really understand something fundamental about functions and their inverses. So I'm going to draw you a little picture. Remember when we have a function, this is the old school when we first start talking about functions like a machine. Function takes things here and sends them here, right? So this is the domain, right? And this is the range of f, right? Of f. That's the domain of f. Where's the inverse function on this picture? Well, it's the one that sends these back, right? The inverse sends these back. So what is the domain of this function? It's the stuff over here, isn't it? Which is actually the range of the f function. So the domain of the inverse function is here, and the range of the inverse function is here, which means that these just switch places. These switch, right? So the domain of the inverse, right? The domain of the inverse is what? 0 to infinity, and what's the range? Negative infinity to infinity. Y'all see it? You can also see it graphically. Let's go back to where I graphed the two together. Look at the red one. Look at the red one. What's the domain of the red one? All real numbers. What's the range? Only from 0 up, right? But what about the blue one, which is the inverse? What's the domain? Well, there's nothing over here, right? There's no graph. There's no blue graph over here. The blue graph starts where? At 0, right? Well, actually doesn't. It looks like it has a what there? Vertical asymptote. So it starts, the domain of the log function there is from 0 to infinity. And what about the range? Look at the blue. The blue goes down forever and up forever, doesn't it? So does that help you see that they switch places? They switch? Yeah? So whenever you have a logarithm like this, whenever you have a logarithmic function, it says there in our notes, I'll put it back up there, it says here that the domain of this, that the x must be greater than 0. You can only put positive numbers in there. There's another way to see it. If that doesn't work for you, this is the last way I'll show it. If we take, let's go back to that example, x 2 to the x, and then we had that other table, it was x log base 2, right? Remember when we did that table? What were the numbers we plugged in here? -3, -2, -1, 0, 1, 2, 3, right? Every number over here that we got out was positive, wasn't it? 1/8, 1/4, 1/2. Everything that came out over here was positive. These were both positive and negative. So when we do the inverse switches them, right? So now these are all positive, and then these are what? -3, -2, -1, blah, blah, blah. This can be anything. So you can see here that the domain is just positive numbers, things greater than 0. The range is pretty much anything. All right. I hope that that's sufficient for you to understand. All right, this next example right here, what we're going to do is we're just going to practice doing something. It's going to be a skill that we're going to need. I think you'll find this to be pretty easy. Whenever you have expressions that involve exponentials or logarithms, you can always convert from one form to the other. So these examples we're going to do are just practicing using this new notation. So we're going to start, let me do, the first one there. If I write 1.2 to the third equals m, I would like for you to convert this to its logarithmic form. In other words, you're going to write down a log, and then the base of this log will be the base of what you see over here. So what's the base in this equation? 1.2. And then you'll have an equals here. I need to put something here and here. So think about the loop, right? Think about the loop. What would go here? 3. What would go here? M. Okay, so these two expressions are equivalent to one another. This is called the logarithmic form. This is called the logarithmic form. I'm just going to put log form. And this right here is called the exponential form. I gave you exponential form, converted it to log form. That's it. It's just practice doing that. That's all. Let's do the next one. Okay, e to the b equals 9. Let's convert that to log form. So I write down log, right? And then I put what base? E. And then I always like to put the equals and then think about the loop. So I always like to start with the right side for some reason, because the loop, right? E raised to the what? B, and then that means it has to be equal to 9. We're not trying to find out what this is, okay? We're not trying to figure out what this is. We're just trying to make sure we know how to convert the forms. Okay, last one. A to the 4 equals 24. So log what base? A. Okay. A to the 4 equals 24. All right, the next set of examples asks us to go the other way. I give you the log form, you give me the exponential form. So log base A of 4 equals 5. These are easier because you just do the loop. Just do the loop and you're done. So the loop is what? A to the 5th equals 4. Next one. Log base E of B equals -3. Convert it to exponential form. E to the -3 is B. Is this simple? Just give you 1,000 of these for your final exam?
Yes.
Okay. Log base 3 of 5. Did you hear the way I said that? Log base, whoa. log base 3 of 5. Log base 3 of 5. Log base 3 of 5 is the way I say that. Log base 3 of 5 equals c. So is it c to the third power, 3 to the c power, 5 to the c, c to the 5? 3 to the c is equal to 5. All right. All right. We're sailing now. We're sailing. Now what I'm going to do is I'm going to give you some logarithmic functions that are more than just log base a of x. I'm going to shift them, move them, put different things in them. And we're going to try and find the domains. Domains of log functions are very important. It's a very important concept. So for this first one, I'm going to give you capital F of x equals log base 2 of x plus 3. And the question for all of these is for you to find the domain. So the domain of a log function, right? We already said that you can only plug what into log functions? Positive numbers, right? Whatever gets plugged in must be positive, which means for us, this right here, do y'all know what you call the thing that gets plugged into a function? There's a name for this in math, and you'll hear this a lot in pre-cal. The thing that goes into a function, this is an expression, right? The thing that gets plugged into a function is called its argument. It's called the argument of the function, all right? So you see this little argument here? The argument of the function. What I need for this function, right? Because it's a log function, I need the argument to be greater than 0, right? Whatever's in there must be greater than 0. So I'm going to write that down. I need the argument to be greater than 0 because whatever this turns out to be better be positive. Because if it's not positive, the logarithmic function can't handle it. It's not in the domain. That's an easy thing to solve, right? Subtract 3, you're done. And let's look at that on a number line. Here's negative 3. This means everything bigger or smaller than negative 3? Bigger. So to the right, all of that. Do I include negative 3 or not? No. Open hole. So the way we would write that is negative 3 with the parenthesis on it to infinity. That's your domain. As long as you plug in a number from negative 3 on to the right, as long as it's not negative 3, that function is in business, right? I'm going to show you. I'm going to graph that function, all right? Just so you can see it. Save this. Let's get a new one. Which one? Oh, it was 2. Oops. Okay, there's the graph of that function. Right, there it is. And you can see that at there's x equals negative 3 in blue. The graph only exists to the right of that, right? The graph only exists to the right of negative 3. All right, next one. I'm going to put this one on the board. This will be a quiz that you have to do right now. No, I'm kidding. I'm kidding. Just trying to wake y'all up a little bit. Should we just do a quiz then? That sounded like enthusiasm. Was that the enthusiasm? G of x. No, but I'm going to run to the restroom real quick. So I want to see if y'all can figure this out. Take a few minutes, talk to each other, help each other out if you need to. No quiz grade or anything. But see if you can find the domain of this function. And I'm going to be right back. I'm going to start working it out silently up here, and then you can kind of see if y'all are even on the right track. What's that called? We've studied this. It's going to be on your next test. A what? Rational inequality. And we have a set of steps to do this. Anyone want to tell me the first step? I'm just following what I showed you. You might have another way. No? Turn it into an equal.
Yeah.
First. Okay. Turn it into an equals first. Then? First, remember that a fraction can only be 0 when the top is 0. So we look at that first. We say, okay, set the numerator equal to 0. And what will that be? -1. Something interesting is happening at -1. First thing. Next thing we do is we say, well, this thing won't even be defined when the denominator is 0, right? So we set the denominator to 0. And we get what? 1. Positive 1, right? Bring the x over. Trust me, it's in your notes. If you took notes, it's in your notes. We did this. Anyone remember the next thing? I've got these two important numbers. You'll know what I'm doing?
Unity domain is -1, 2, 1, unison, 1, 2.
Maybe. Yeah. How, did you do this? Did you do a number line? Yeah. Okay. That's exactly what you have to do now. Number line, that breaks your region up into 3 regions, and now you pick test points. Test points here, here, here. Where am I? What test point should I use here? Negative, what, 2? Good one there. 0 and 2. And we're going to plug those numbers into the original and see if it's true or not. Okay? So let's try -2 in there first. I'm going to put it right under here. If I do 1 plus -2 over 1 minus -2, the question is that greater than 0? So what's the numerator? -1. And what's the denominator? 3. Is a negative number greater than 0? No. So I'm not going to include that region. How about 0? Let's try 0 in there. 1 plus 0 over 1 minus 0. Is that greater than 0? So that's 1 over 1. That's 1. That's greater than 0. That's true, right? So I want to include that. Now I try 2. 1 plus 2 over 1 minus 2. Is that greater than 0? So the top is 3. The bottom is -1 greater than 0. Is negative number greater than 0? No, doesn't work, right? So far, it's everything between here and here, right? So far. Do I include -1? Well, where did -1 come from? It came from here. It came from setting the top equal to 0. The top equal to 0 makes this equal 0. Do we want it equal 0? No, so we don't want -1. How about 1? Do we want 1? Well, 1 is when the denominator is 0, and you sure as hell don't want the denominator to be 0, ever. Regardless of the logarithm, we don't want it to be 0, right? So this. So it's just the stuff between -1 and 1. That's the domain. The domain of this is -1 to 1, not including the endpoints. Yeah? I'm going to graph this for you. When I graph it, the graph should only exist between -1 and 1. It's going to look weird. So x plus 1 over x minus 1. It was 1 minus x, sorry. 1 minus x. And this, just ignore what I'm typing in here. Just look at the graph. That's all that really matters. Okay, there is the graph of this. Does that look like a logarithmic function? No. Do you know why it's not? Because this is not just a logarithmic function. This is the composition of two functions. Remember the f of g of x thing? That's what we have here. The inner function is what? A rational function, and then the outer function is a logarithmic function. So when you put a rational function into a logarithmic function, you do not get the nice logarithmic graph. You get something different, right? So, yeah, you get it, domain? Let's see if the next one's worth us doing. That's an interesting one. I think it's worth us looking at. H of x equals log base 1/2 of the absolute value of x. I think we might be able to just figure this out without writing anything down. What has to happen with the log? This right here, whatever's in here, must be what? Positive, right? Is the absolute value of x always positive? Yes? Careful? There's one place it's not positive. At 0. Right? What's the absolute value of 0? 0. And is 0 bigger than 0? No, 0 is 0. So the domain of this should be everything except 0. How do we say that? -infinity to 0, not including 0, union 0 to infinity. I did that just by inspection, just by looking. I would like to graph this one. Whoa, crazy graph, right? Look at that graph. You have a vertical asymptote. It's a vertical asymptote. If you zoom in, there's always a gap in here. All right. Is that all right? Okay, we continue. So I've already discussed the graphs of these, right? I've already discussed the graphs, what they look like, reflections. Yeah, I'm not quite ready for that. I want to do one more thing before I do that. I want to do a recap of where we are with log functions. So real quick recap. If we write f of x equals log base a of x, this is just some function, right? Now we know this is the inverse of something else, but just by itself, it's a function, right? By itself, that's just some function. And we have some conditions here that I didn't talk about before. This a, that base, didn't that come from the exponential function a to the x? And weren't there some restrictions on that a back with the exponential functions? What was the restriction on the a? Can't be 1 and it has to be positive. Those restrictions are also implemented here. You cannot have a base that's something other than a positive number, or it can't be 1 either. Okay, so as long as this base is some positive number and not 1, then this is defined. The other important thing that we should know is that the domain, right, is 0 to infinity, which means whatever's in here, right, has to be positive. We know that the range of this is what? What's the range of that function when you graph it? Everything, right? Negative infinity to infinity. All right, I didn't mention this before, but when you graph this, we're going to have one of two things happen. It's either going to look like this, or it's going to look like, oh, I did that wrong, sorry. Or it's going to look like this. Now, where am I getting those from? I'm getting those from the fact that this is the inverse of an exponential, right? And we had two different types of exponentials. We had growth, right? We had growth, and do you see it's a reflection? And then the other one was what? Decay. Now this one's a little harder to see, but that is a reflection over the identity. Can you all see the reflection there? So in this case, can you tell me, do we have a vertical asymptote? On this one, do we have a vertical asymptote? Yes, we have a vertical asymptote where? At x equals 0. In both of these, don't we? In both this black one and this black one, we have vertical asymptotes. With exponential functions, we had what? Horizontal at y equals 0. What else? Domain. This point right here and this point right here must exist on both of these. Do you remember with exponential functions, there was a point that was on both of them, on all of them, no matter what? What was the point here? 0, 1, right? So this one is going to be 1, 0. 1, 0. 1, 0. Right? That will be on every logarithmic, well, every basic logarithmic function will have the point 1, 0 on it. One last thing, promise. This is like logarithmic growth, and this is like a logarithmic decay. But it's not the same as exponential. Like, we don't treat it the same way. Like, exponential means really fast. We don't do it the same way with logarithmic. But do you agree that as I move to the right, this graph goes up? This graph goes up slowly, forever. And then as I move to the right on this one, it goes down, down, down. All right, that's it. So let me give you, before I show this next thing, I want to give you the history behind it first. There is is that a question? No? No? Okay, all right. So that is our generic formula, right? Yeah, let me do it this way. I told you about two special exponential functions last class, two special ones. Do y'all remember what they were? The two special exponential functions were, the first one was f of x equals, do you remember? 10 to the x, 10 fingers, right? Remember that? And then the second one was f of x equals what? E to the x, and that's the one I told you was very special in calculus, right? These were our two special functions. Well, if these are so special, right? If they're so special, then their inverses should be special as well, right? So what is the inverse of this function? The inverse of this function should be logarithm, what base? 10 and then x, right? That's the inverse of that function. What's the inverse of this function? Log base e. Log base e of x. Right? Those are the two inverses of those two very special functions. Now here's where human beings came in and screwed everything up. What happened was, historically, these functions were coming up in so many different places. And when I say that, I mean like throughout the last couple of hundred years, researchers, mathematicians, physicists, chemists, biologists, they're doing research. They're using these functions all over the place. They're using these functions all over the place, and they're writing papers, right? They're writing papers, research papers that they're sharing with one another, saying, hey, look, I'm discovering this about, acids and concentrations of acid in a solution, and you take this logarithm, blah, blah, blah. And so within this, 400-page paper that they publish, they have these expressions showing up hundreds of times within the paper. So back when typewriters were around, do y'all know what typewriters are? I'm not trying to insult your intelligence, but have you ever actually used one? Has anyone here ever used a typewriter? You have? Yeah, like the one that has a little metal thing that goes that? Okay. So the old school typewriters, when you were typing, right, it would have this little arm that would come up and stamp ink onto the page. If you had to write if you were writing a research paper, and in your paper you had all these mathematical expressions, and you had to bring in this logarithm, which came in many places, you would have to do subscripts, right? So subscripting on a typewriter works like this. You're typing, you stop, you turn the drum a half click, you hit E, and then you click back, and then you continue typing. Imagine having to do that hundreds of times. It'd become